Here are solutions to homework set number 6 for ECE 463-663 Modern Control. Now, in this assignment, it's try to find a feedback control law to stabilize a Cartan pendulum in a ball and beam system. So here's what I'm trying to do. I'm balancing a yardstick on my hand, basically. I want to know what is the force on the base to get it to go to your set point, in this case +1. So get it to move over without falling. How do you do that? Well, here we're going to be using Bhaskara, or pole placement. First comes down to the requirements. The requirements are I want a DC gain of 1, 2% settling time of 10 seconds, and 5% overshoot. The 10-second settling time says that for your pole, the real part of the pole, is 10 seconds. And so the real part of the pole is at -0.4. That gives you the 10-second settling time. 5% overshoot tells you the damping ratio. Damping ratio of 5% means the damping ratio should be 0.6897. Or I know the real part, I know the angle, I can find the complex part. Your pole should be right here at -0.4 plus j 0.42. That should give me 5% overshoot. So using pole placement, what I do is I input the system's A matrix, B matrix, check to make sure it's controllable, and it is. Now place the poles. Put the dominant pole at -0.4 plus j 0.42 and its complex conjugate. The other two poles are kind of arbitrary. Just stick them out of harm's way. I stuck them at -2, -3. Anything around there works. When I do that using pole placement, I want to put what my feedback gains. If you check the eigenvalues of A minus BKX, those should be where you put them. And they are. Just didn't show it. To find Kr, Kr makes the DC gain 1. So find the DC gain without Kr, adjust it so the DC gain is 1, so here's Kr. So there's my feedback gain Kx, and there's my feedback gain Kr. So let's see how that works on the linearized system. Forming the closed loop A matrix, closed loop B matrix, C and D, just look at the output. Take the step response and plot it. And here I plotted the step response along with 1. The DC gain is 1 and 1.05, showing 5% overshoot. So I designed for 5% overshoot, 10-second settling time. I got 5% overshoot, 10-second settling time. Looks like that's a good control law. The acid test is try it on the nonlinear system. So basically these are the two lines of code that I have to modify. The feedback gain Kx and Kr, and then this line. I'll then define the input as being Kr times R minus Kx times X, and pick the set point to be whatever you want. So let's see that in action. Here I'm going to go from -1 to +1 for my step. At 15 seconds, I'll then tell it to go back to -1. So the control law is working. It is going to your desired set point with a gain of 1 and keeping it balanced. And in addition, there's 10% or 5% overshoot that you can see. It hits the target and overshoots a little bit. This little undershooting right here, where it goes the wrong direction, that's just how the inverted pendulum behaves. To get it to go right, I first have to go the wrong direction, get it to start leaning, then I can catch it. So that was problem 1. Second problem is repeat for a ball and beam system. So let's see how the ball and beam behaves. In this case, I've got a ball riding on a beam. I'll apply torque to the beam to get the ball to start rolling. And I'll then turn the beam up to get the ball to stop. And I want it to stop at my set point plus 5%. So there's the overshoot. And it should come back. So that's what I want to do. How do you do that? With pole placement, it's really the same algorithm. Once I've got the A and B matrix, it's use pole placement to place the closed loop poles. I can put them anywhere. In this case, I want the same response. 10-second settling time, 5% overshoot. So same spot for the dominant poles. Find the feedback gain Kx, and then add Kr to make the gain 1. So, same procedure as before. Input the A matrix for this system and the B matrix. Place the poles. You have your feedback gains. Pick KR to make the DC gain 1. And voila! In MATLAB, I can check the linear system. Here's the linearized A, closed loop A matrix, closed loop B matrix. C and D stay the same. Plot the step response, and this is the step response. Output goes to 1. This is plus 5%, showing I've got 5% overshoot. Everything looks good. Now try it on the nonlinear system. So again, the nonlinear system is what we're showing here. As I run it, it goes to the target, plus 5%. Okay, so again, pole placement is really the same algorithm over and over again. The last one is a double pendulum. So with the double pendulum, here's what it looks like. If I just do a PD control, I've got a force on the base, I've got a pendulum hanging a pendulum. If I just do a PD control, feedback position times 10, the derivative of position by 10, I get this response. Kind of oscillatory. Can I do better? And the answer is, yep, I sure can. That's using pole placement. So same procedure as before. Here's my A matrix. Here's my B matrix for the open loop system. Find the feedback gains to put the dominant pole so that the settling time is 10 seconds, 5% overshoot. Again, same procedure. Input the A matrix. Check the eigenvalues. B matrix is controllable. Place the poles at minus 0.4 plus or minus j.42 gives me 10 second settling time, 5% overshoot. The other poles are kind of arbitrary. I just stuck them at 2, 3, 4, 5. Do that, I get my feedback gains, checking the closed loop poles are where I put them, so everything looks good. Find KR, so the DC gain is 1, and there's my control law. Now I can check the linear system. If I linearize the system, here's the closed loops A matrix, B matrix, C and D. In this gets me just looking at position. Take the step response, and again, everything looks good. 10 second settling time, 5% overshoot. Now let's try the nonlinear system. So here's the step response with just a PD control. Kind of see it's kind of squirrely. Plug in those gains that I calculated using Bhaskara, or pole placement, whatever your favorite name is, and try it. And it comes over from 0 to plus 1. Has a little bit of overshoot, 5%, and comes back. And notice the response is much, much better. I'm no longer getting that squirrely response that I got with just a PD controller. So that is basically homework set number 6 for 463, 663, pole placement. Once I have the dynamics, the procedure to find the poles is pretty straightforward. Just throw it in your pole placement algorithm, give it A, B, your desired pole location, and the gains drop out. Homework set number 6 for modern control.